Good afternoon, everybody. My name is Sean Smylie. I'm Vice Chairman of the JCT Council, and thank you for joining us today in this annual JCT Povey Lecture. The JCT Povey Lecture is an annual event at which an eminent person is invited to give their views on significant matters which are relevant to the construction and property industry. The purpose of the lecture is to stimulate and encourage ways of improving the output of the construction industry. The event was first inaugurated in 2003 to pay tribute and acknowledge the works of Philip Povey, who served the JCT for over 50 years. Philip John Povey was the first Secretary General of the JCT Contracts Tribunal. He was a barrister by profession, and he entered the construction industry via the NFBTE, where he was legal advisor. The NFBTE later became the Construction Federation, and Philip progressed to eventually becoming the Director General of the Construction Confederation. It was in this role that he became involved with JCT and assisted the joint secretaries of the JCT to draft contracts. He later became the first Secretary General of the Restructured Joint Contracts Tribunal in 1998. He was an extremely gifted draftsman and often satisfied the demands of various disparate and competing bodies. Although there were committees and working parties and individuals who provided assistance in the drafting of contracts, it was Philip who shouldered most of the burden of writing the text. Our speaker today is Diego Phillips, Director of Decarbonisation and Innovation for Building Structures at WSP. In this role, he works towards creating zero carbon buildings to address the climate emergency. He has led the creation of WSP Structures Decarbonisation Roadmap and continues to deliver on its commitment to halve the emissions of their design and advice by 2030. As a structural engineer, Diego has wide experience in construction of tall buildings, complex basements, office refurbishment, and cultural venues. He was lead engineer for the design and delivery of 22 Bishopsgate in London. Diego will today discuss the transformation power of automatism and AI in the design of better buildings. The title of Diego's presentation is Human-Centered, Evidence-Based, Augmented Intelligence in Building Design. Before I hand over to Diego, the audience will have the opportunity to ask questions at any time by typing their questions into the box under the video itself. Thank you. I would like to hand over to Diego to commence his presentation.
Thank you, Sean. And thank you everyone for joining today. The title of the talk is Human-Centered Evidence-Based Augmented Intelligence in Building Design. I'll explain that in a bit more detail in a minute. But if you think about the words in that title, it's about us, it's about humans, it's about centering design around humans. And it's also about creating evidence to inform designs and inform construction better. So keep that in mind throughout the presentation. A little bit about myself. I'm a structural engineer. I work on tall buildings in the UK and in the Middle East. My experience is very diverse, different types of buildings, all the way from the most complex to the smallest projects. At the bottom of your screen, you see a tiny little tree. That is possibly one of the most challenging projects I've worked on. It is a 1,000-year-old oak tree in Liverpool that needed propping and supports to make sure that it could stand up for the next 200 years. And that was more complex than any tall building I had ever designed before. For the last 5 years, I've led WSP Structures decarbonisation efforts. So we realized that the real impact that we could make as designers was in the emissions from the buildings that we design. Everyone is focused on their own carbon footprint. This is what we call a carbon handprint. What you can design for a client. We realized that that is where we could make the biggest impact, and I've been leading that. One of the things that we created as part of this journey is a process, a digital process that I'm going to show you today. And then that got me into creating tools to decarbonize our buildings and to help engineers create better buildings and do better processes. And that is how I got into automation and AI. So hopefully today I'll tell you a bit about all of those things so that you can see how automation, AI are already changing our industry. It's such a fascinating industry, and it's incredible because we can really make a difference. The buildings that we design, the buildings that we create, they change cities, they change people, they change lives, they change us in return. And it's important that we realize how impactful this can be. Before we go into a bit of detail, just let me tell you something. AI is already here and automation is already happening all around us, and it will transform how we do things. All the way from optimizing buildings from an early stage to enhancing our creativity and how we design and how we create things, to creating new building materials and more sustainable buildings through automation, through iterations, through optimizations, but also how we design buildings and how we build them, how we go on site, how we go around them, solving those problems. At the same time, it is something that it will democratize access to skills, because more people will have access to similar skills, which means that we can build things together. So it's something that is already changing how we do things, and we have to embrace the power of being able to iterate and optimize something at an early stage. Today, during this talk, I'll talk to you through how we are optimizing buildings from an early stage to create the most efficient solution. It's going to change how we build things as well. If you combine the power of automation, the power of AI, and the power of robotics, we could really challenge all those construction paradigms that we have right now. I once read a really interesting prediction that someone said that by 2040, we would have robots with human dexterity at the price of a microwave. If that is true, then that means that the construction industry will be completely transformed, since we have that different workforce that can do buildings in a different way. The challenge, though, is how do we respond and how do we adapt quickly enough, but also making sure that these changes come with consideration to people, consideration to the processes that we follow, to health and safety, well-being, etc. It's important that we remember that when we think about automation and AI, we need to think about upskilling, not de-skilling. So thinking about AI as a tool that can help us enhance our intelligence, which is why today's talk is called Augmented Intelligence. It is about people, and it's about augmenting what we can do to deliver better projects. And before we go into the most interesting part of the presentation, there's some predictions here that some colleagues thought about for the next few years. How in the early 2030s, AI and generative AI will help us optimize buildings from an early stage, looking at more efficient buildings, and then it would also help us create better materials because we can test more elements without having to go through certain processes. And as we go into the 2040s, we will begin to see automation in construction sites. And then how can we predict the 2050s and beyond with the anticipated establishment of general AI, etc. So the point here is not to try to predict the future, is to respond and adapt as it happens, because it is exciting. What's coming into the construction industry is absolutely fascinating. It's going to change how we design, it's going to change how we build, and also it's going to change how we live and work within those buildings. So that was just a brief introduction to the challenges and the interesting part of AI in construction. And now I'll focus on what I do, which is design. When we think about design, the importance of creating good buildings is fundamental, and we would like to achieve sustainable outcomes. sustainable buildings are fundamental, a key to addressing the climate emergency, to addressing the changes that are coming in the following decades. But to achieve true sustainability, we know that we have to go beyond sustainability itself. We need to create buildings that can restore the environment, that can regenerate it. So that combination of regeneration and performance-driven design is what we see as the key to achieve true sustainability. What is performance-driven design? It is designing buildings to meet certain KPIs, to achieve certain performance simultaneously. And I'll get to that in a bit more detail. I just want to explain this briefly, these concepts, so that you can think about where the title of the presentation comes from. It comes from bringing together regenerative design, performance-driven design into what we call performance-informed, human-driven concepts. It's about humans driving the performance of design of buildings to achieve a more sustainable outcome. If we then combine the power of artificial intelligence with our intelligence, that is what we call augmented intelligence. So from these three concepts, to achieve sustainable buildings, to use our human intelligence, to use performance-driven processes, this is where the whole idea comes from. Now that you have that in mind, I'll explain in more detail exactly what the process is about. The first thing is that the context of today demands buildings that perform better. So we normally hear about the three variables, the three performance KPIs in building design: time, cost, and quality. And we even make jokes about how you can only have two of those at the same time, because it's impossible to have the three of them. Actually, let me tell you something. The current context in design and construction has to go beyond that. Our clients now expect buildings not only that have good quality, that can be delivered in a good time, and also are good, have a cost that is good. They also expect us to perform in terms of other building scale KPIs, such as embodied carbon, operational carbon, building performance items. But even go beyond that, which is about place-making concepts such as circularity and thermal comfort and connection to the outdoors. Our clients are expecting us to create buildings that achieve all of those KPIs simultaneously, and they are all interconnected. And that is the challenge of building design. And I'm going to pause here for a moment to ask you a question to think about when you think about building design. I know you might not be designers, but just pause for a moment and think about, what would you do? If you have the same brief, let's say a 20,000 square meter office building, and you are an architect, and the client's brief is design the building with the best amount of daylight. That is one challenge. Now, some of you will be the structural engineer. Think about being the structural engineer, and the client's brief is, how do you design the most efficient building in terms of concrete, the least amount of materials? And then some of you might want to choose to be the mechanical engineers. Your objective is to optimize this building in terms of energy consumption. Now, think about, if you are optimizing in your role as an architect, structural engineer, or mechanical engineer, your idea is to optimize those parameters. What will the building look like? So think about that for a few seconds whilst I run this animation. That is what we did. So we created 3 separate algorithms. This is all about introducing, augmented intelligence into the design process. We created 3 algorithms to optimize buildings for those 3 parameters, 3 performance indicators. And of course, as you might suspect, the results, they are completely different. And this was the eureka moment, when we realized that if you look at the building on the left, That looks like it looks like this because to optimize daylight across the floor plan, you have to have a narrow floor that you can get daylight into the depths of the floor. And because you want this narrow floor plan, you will have to build up, and then you have a tower. It looks like a tower. If you are the structural engineer and you want to optimize in terms of materials, the one on the right is the one that will use the least amount of concrete. Shallow foundations, it is almost like a campus-style building. But is that good for daylight? Surely you don't get any daylight in the center of a floor plan. And it's not very good for energy either, because you get all these solar gains on the roof. And if you're optimizing only for energy, you want to isolate the building completely from all the elements. So then you end up with a basement box, completely isolated, no thermal losses. But this building is not very good as a building. It's not very good as an office building. It hasn't got very good daylight. And in terms of embodied carbon, using concrete, basements use a lot more concrete, a lot more materials than the other options. So what this is showing us is that the design process, if done in isolation, if optimization is done in isolation, it leads to different outcomes. That means that the three main disciplines in building design, architecture, structure, and building services, constantly pull in completely different, completely opposite directions. That is the challenge of building design. How do you bring these disciplines together? A typical design process looks a bit like this, where one discipline comes before the other ones. And this is why buildings look the way they look, because decisions are made almost in a sequential way, and one decision follows the other. Actually, normally, it looks a bit more like this, where one discipline is the central one that drives most of these decisions. So with this linear process, this linear decision-making process, trying to optimize a certain variable in that process is actually a real challenge. And when you try to optimize one, you might find that the others actually are impacted negatively. So what is the solution? So what we thought as a multidisciplinary design firm was, we need to optimize buildings for more than one variable simultaneously. And this is what led to this transformation. This is what we created a couple of years ago that has really changed how we design every building. We combine those three algorithms. And those three algorithms are now testing for each combination. It's generating a different massing, a different shape for the building, as you can see on screen, different shape, different type of window, different size of window, different orientation. And every time each of these volumes is created, each of these buildings are created, you can evaluate performance in the X, Y, and Z axis. In this case, the three objectives that we defined: embodied carbon, operational carbon, and the amount of daylight. So evaluating a building simultaneously hundreds of times. And this is the key difference. Traditionally, during concept design, that is when we have the least amount of fees, which is why there is not that much science and engineering going into the design process. So that is restrictive. But with the power of automation and with the power of AI and a few machine learning processes, we can streamline this and really create thousands of points of data at an early stage. Each of the dots that you see on the bottom left of your screen is a different building that was simulated, analyzed for these parameters. Not to the level of detail of a completed, building, but to a level of detail that is good enough to give an indication of how the building will perform for those indicators. And then we bring this to the client and we help them see how, by filtering those results, you can achieve the performance that is expected from the brief. And now you have a variety of buildings that can do that. This is what we call the co-design framework. And the co-design framework is the fundamental behind a design process that is performance informed. This is the key difference between what we are doing now and how concept design was done before. Before, concept design was typically a professional having an idea, coming from experience or coming from judgment. Now what we're using is supporting those ideas with evidence. So if you allow me to read this, because it's a bit of a mouthful, co-design is a systems-level integrative design approach that unites multiple disciplines to collaboratively address the complexities of whole building performance. In summary, it's about the entire building. It's not just about one discipline, it's about all the disciplines. And it's about integrating them to evaluate them simultaneously to improve the performance of the whole building. I know it sounds obvious, but it's actually something transformational. And it's founded on 3 principles. First, multidisciplinary collaboration. Second, early stage asset simulation. And third, evidence-based decision making. In other words, more than one discipline, building services, building structures, architecture. Simulating, so it's not just about intuition and experience, it's about actual computer models that give you the performance of a building in different situations. And third, using all of that data to truly make better decisions, which that will then transform the design process from that linear process that we saw before to something that is a bit more collaborative, where all the disciplines can, and we can see how each discipline affects each other and make decisions that benefit the whole project. So this is the theory. So how do we apply this in practice? I'll show you a few designs. And the reason why this is interesting is because sometimes the impact of one variable on another variable is not intuitive. And you'll see this, hopefully you can follow me on this simplistic example. Let me click. So the client's brief was, I have these apartments in this tower and I'm struggling because the daylight assessment for planning, it's telling me that I need bigger windows. And if I create bigger windows, I'm letting more radiation from the sun come in, brilliant for daylight, but not brilliant for overheating, because the apartments are overheating because the temperature inside is going up. That means that I will need to introduce mechanical cooling, air conditioning into these apartments. So it's outside of the brief. So the solution is to increase the window size, but also put a film in front of some of that window so that we can reduce those solar gains. So it's leading to a perverse outcome because you're increasing something that is supposed to be good, and then you're covering that with something that is not so good. And it doesn't converge into one acceptable solution. So they asked us, please help us solve this puzzle. And that is why we created the first analytical model, where we evaluated each of the windows as a different variable. The window size, the depth of the threshold, the type of glass, the type of shading, etc. And each of these iterations that you see on screen changing, they represent a dot in the graph of performance with these 3 axes plus a 4th one. So we are evaluating 4 parameters, 4 criteria at the same time. And then the result that we gave and the advice that we gave to our client was actually not intuitive. It was contradictory. It was the opposite of what someone would have said. We said, actually, you don't need to increase the window size. You need to reduce the window size. And you are going to get, by changing the type of shading from that film to a different sort of element, like the louvers that you see on there, you'll get the same or more daylight, and you will reduce the amount of overheating. And that is a result that you would have never arrived at if you had followed the linear process, because the linear process determines that one consequence follows a certain cause, and you never lead to that iterative approach, which we have achieved here. So the client was quite happy, and then they came back to us and said, all right, help me with this other tall building. And I'm also struggling because we want to have as big as possible windows across the entire perimeter. So we took one floor. This is one floor of a 40-story tower in London. And we created a model, a parametric model, where each of the elements, the type of balconies, the shading elements, the size of the window, the thickness of the windows, the type of glass, they all represented a different parameter. And we created these hundreds of points of iteration and evaluated them. So if you're familiar with building design and conceptual design, in conceptual design, you typically have 2 or 3 options that the design team evaluates, and then you choose one and you carry forward to the next design stages. What we have now is 1,700 options, all of them covering what we call the design spectrum. You have all of this, and then what you can do with all of that data is many things. One, you can train a machine learning model, because you can then extrapolate and interpolate, so you can fill those gaps to complete the surface of the design spectrum. Now, in the past, design was 2 or 3 options based on the architect's intuition, on the engineer's experience, and the client's needs. Now, all of those decisions live in this surface of possibilities. And what we do is we help the client by filtering those design solutions. So on the next screen, you'll see how we start filtering. First, through performance along the x-axis, and then through performance on the y-axis, until we achieve elements who meet the brief. So all of those dots, all of those dozens of dots, meet the performance brief in every axis, and then we can see how different they are from that blue dot and that red dot. The red dot was the original design by the architect. The blue dot is what we ended up with, but because we had to make the conscious decision to compromise some of those. The interesting thing is that building design now becomes a process where you start with the most efficient, possibly efficient solution, and then you make those decisions to achieve what you really want to achieve. And we're supporting clients by giving them all of those tools and creating a catalog of the interventions that they need to do on each facade, for example, to achieve that. So that was a very successful project, and we ended up using a combination of different types of facade and different types of shading devices and balconies to achieve that balance that led to that blue dot on the previous screen, which was the solution that was chosen by combining all of this evidence, which is why it's called evidence-based design. And it's called human-centered because this is humans making those decisions, and it's about how those decisions affect thermal comfort and affect how we interact with the building. This is how we see the future of the industry, by creating designs that respond to a combination, an optimization of different processes. So then the next example is similar, but it's bigger. In this case, the client they had already a master plan with a group of buildings. It taught us that typically when you design a master plan, there's other decisions that come first. These decisions are, for example, where roads are. So you have to respect the infrastructure. So the buildings couldn't really change their shape or their position. The only thing that we could change was their height. And the client came to us and said, how can I optimize these buildings? I'm struggling with the amount of daylight that I get in some of the buildings. I'm struggling with the costs of the operation because it's leading to a massive amount of energy. I want to reduce the energy used in the building. I want to increase the amount of daylight. I want to reduce the potential of overheating so I don't need to introduce air conditioning or mechanical cooling. How do you find that? So we asked them, what can we play with? And they said that the only thing we could play with was the height of the building. So this is why we created what you can see now on screen. It's a model that plays with the height of each of these elements, each of these buildings. And every time it varies the height, and it doesn't vary the height randomly. It uses a genetic algorithm to find the best combination after each generation, which is why you can see that all of the results are combined in a group that makes sense and not just completely dispersed, because the algorithm is pointing them in that direction. And then with these hundreds of different options, every time there's a different building height, we evaluated all of those parameters. And then the conclusion from that assessment was actually quite similar to the original design. It was just a few minor tweaks that you can possibly just barely see here on the left. That building is a little bit shallow, lower than that one. This one is higher, etc. Small changes that led to better performance because we could analyze the interaction between those buildings. We reduced the operational energy, the operational carbon of the building, but actually there was an unexpected win as well, which was a parameter that we didn't think about, which was the overall surface of the volumes, which translates directly onto area of glass and facade. We've managed to reduce that, resulting in nearly £500,000 of savings because they had to build physically less surface of building. So that saving was many times more the cost of this assessment. And that is what really adds value to a project. At an early stage, being able to optimize a building to that level of detail was absolutely transformational. So then this client came back again to us and said, now I want to do this, but looking at every single apartment. So that is one of those buildings in the same complex. And they wanted to look at what happens with each apartment. So we created a parametric model for each apartment, each cluster of apartments. You can see the colors means a cluster. Some of them are north facing, some of them are south facing, some of them are in corners. So depending on where they are, they had a different category of apartment. And we created all of those results, and then we can analyze them all. And you bring them all together, and then you can see what improvement means on that graph, because you try to bring them as close as possible to the origin. And that is how we start making decisions to really improve each type of apartment depending on where they are, because the solutions will not be the same for different types of apartments. Again, it's something that sounds really obvious, but it's something that never happens. When do we have the opportunity to introduce savings like this? It's typically at the end of stage 3, when we want to do some value engineering. And by then, the amount of value engineering, and I'll go back to that point in a second, that we can really introduce is not that great, because all of those big decisions, like the height of the building, the orientation of the building, they were already made. So through this analysis, which was done at a really early stage, at concept stage, we managed to determine different interventions for each type of apartments. To improve daylight, changing the window sizes. If it was a west-facing apartment, it was a different intervention. But for me, and it's going to sound very geeky, and maybe not everyone will understand what I mean, the most interesting intervention that we came up with was not really related to the window size or the amount of daylight that apartments will receive. We realized that, for example, north-facing apartments, which you can see here in red, they were always failing. They were always failing because they were not getting enough daylight. And if we wanted them to achieve enough daylight, the windows were so big that they would lose too much heat in the winter. And it was just never, and the heating demand was much higher. So we couldn't really find that optimized solution. And we realized that there are limits to optimization. And that led to, for me, a revelation, because we said to the architect, actually, what we need to change is the apartment itself. All of these apartments are typical apartments for the UK. And we realized that that ratio of apartment, of a one-bedroom apartment that is almost like a square, didn't really work. So we suggested to the client to make those apartments less deep, more shallow, so that more daylight could penetrate the depths of the apartment. It would meet that without having to increase the size of the windows. Now, I know it sounds very specific, and maybe not everyone in the audience will understand what I mean. But for me, it was about realizing that whilst you assess some parameters that are within your control in a building, having the possibility of evaluating performance at an early stage made us realize that the parameters we had were not the right ones to be assessed, that we had to influence the design of the building even one step before that, which is the type of apartment. And that just shows how important it is to look at early stage design through the lens of automation and a bit of AI. So that is what we call the new design paradigm. Because currently, building design is about this dream. We all have the dream of a building, the architect's dream, the client's dream. And then we spend the entirety of the design process incorrectly called, in my opinion, value engineering. Because we're not really adding value. We are de-specifying, we're removing cost until we get to the product that we can afford. This makes the design process a journey of disappointment. And it's not great. What we want to achieve is flip that upside down and start with the absolutely most efficient design solution through automation, through the use of AI at an early stage. And then you can make conscious design decisions to increase the cost, to increase carbon emissions, to increase program until you achieve the absolutely best product. And even though you're increasing those elements, this best product will be better than anything that you can achieve through the traditional design process, because you're not starting with the most efficient. That is how we want to change the industry, and I think that is one of the most fundamental impacts of automation and AI. And just to wrap this all up, how is this going to happen in the design industry? And of course, that is directly relatable to the construction industry. Well, the first thing that I need to answer before someone asks the question is that we're not replacing engineers or contractors with ChatGPT. That is not the idea, because those tools are not meant to do what we do. They do something else, and we should use them in the best way possible, but they're not simply replacing us as they are. What the challenge that we have in the design industry, and this applies to every industry, is identifying those processes that we currently do that include as part of a building design. In my industry, structural engineering, they typically are calculations, modeling, detail analysis, reporting, drawing, and creating construction documents. All of those can be automated. The challenge that we have currently is connecting them. So how do we connect those different tools into something that makes sense? Currently, we use spreadsheets. We export data from one system, one software to another, and all of that introduces sources of error. How we see the future of automation and AI in the design industry is first by creating bespoke analysis packages that can help automate each of those tasks. For example, you've got one which is the calculation piece, another one which is the geometry and coordination piece, another one which is the reporting piece, another one the drawing piece. And then following that, we connect them using AI agents. And this is what AI is really good at. It is about connecting data and transferring data and transforming data in an accurate way, and in a precise way and in a fast way. This is how we see AI changing the design industry, by helping us connect all of those processes. And once we successfully connect those processes, when we achieve what we call a digital colleague, an engineer that is supervising a process that has been partially automated and connected through design agents. And when you combine those digital colleagues, that's when you achieve a digital design team, which is the ultimate goal, to make sure that engineers have access to these tools, to put them at the center, which is why the talk today was called human-centered. It is about putting the engineer, the designer at the center, having access to all these different tools so that we can, through analysis, through simulation, through early stage evaluation of buildings, we can really augment our intelligence and really transform how buildings are designed. That was it. Thank you so much for your attention, and I look forward to answering some of the questions. Thank you.
Thank you, Diego. We can now like to address some questions from our audience today. If I can first deal with a question that we received from Roland Finch. Has any research been carried out into comparing the whole building performance and e.g., for example, procurement route or contract choice?
Short answer is we haven't. The focus of our research is on performance within the design part of the process. We haven't compared that against difference in procurement and contracts. But it sounds like the next logical step, understanding how those elements really impact whole building performance.
So would you see it as a sort of an early contractor involvement route rather than a sort of single stage design and build route?
I think that we can use tools like this for different types of procurement methods, and it's about, I don't see that as replacing one or the other. I think that whichever route is chosen, we can use these tools to enhance that process.
Okay. We now have a question from Simon Tolson, who is a well-known lawyer at Fenwick Elliott in London. Simon says, as a lawyer, I ask who is ultimately accountable when a flaw emerges in an AI-generated design solution, the AI developer, the architect, engineer, or another stakeholder? Who's the principal designer?
That is a fantastic question, because it is fundamental to understanding where liability is. And just because something can design a building, it doesn't mean that people will, unless you can clearly understand where that liability lies and who's responsible for it. The way that we do things right now, you cannot blame the AI. The engineer designing an element is responsible for the design, regardless of what tools are used. We could have used Excel, we could have done it by hand, we could have used a piece of software, we could have used an advanced AI generating tool. Ultimately, the responsibility is with the professional that used that tool, regardless of what tool that was. But I think that understanding liability will be fundamental to really see where these technologies are implemented, because someone has to be able to sign something off.
I suspect Simon's question is who do they sue when it all goes wrong?
I think that we have currently clearly defined responsibilities, right? I don't think that's going to change just yet, because we are using different tools. There might be a future where a company creates a product that is a building, and they are the ones signing the process and the product off, and they accept the full liability. And I think that's also a valid scenario. You could appoint companies that provide you the full service, and they will be the ones liable for how it performs. But as it currently stands, I don't think it's changing who is responsible.
Okay, that's good to know. We've got an anonymous question now, which is basically, how is the cost data stroke client's budget considered within the model? That is, how would you work with the client's tool if their optimal solution needs to be value engineered, I assume, to hit the client's budget?
Right. So I don't like the term value engineering because, as I said, we don't add in value. And the fundamental change in this design paradigm is that the reason why we need value engineering right now is because we start with something that we realize it's outside of the budget, and then we want to bring it back to budget. If we create a process like the one I showed you that evaluates more than one variable, in this case, it was evaluating embodied carbon, operational carbon, daylight, overheating potential. But all of those can easily be converted into a cost or time, depending on a few factors. So if you create a process that evaluates those at the same time, you can easily start with an option that is from the early stage below the budget, and that is one of your parameters. And if you don't have anything that from the early stage is below budget, then some of those parameters or some of those assumptions are not right. The project is not viable. And if we start then with a project that is below budget, and that was my point, then we can make decisions to actually increase the cost until we achieve not only the most efficient building, but the best building within our budget. So this is what I meant when I said flipping the design paradigm upside down. We currently do not have the tools to begin to start with the most efficient solution. We typically start up here with sometimes the most expensive solution, and we bring it down. I would like to see the construction industry changing so that we start from we invest more at the beginning, we invest more design fees at the beginning to optimize so that we have the best possible product cost at the beginning, and then we increase that to achieve what we really want to achieve.
It seems to me that what we're asking clients to do is to basically pay more upfront for a more economic, efficient and sustainable building.
In short, yes. The long answer is not necessarily that much more. Currently, the limitations of how much we can invest at the beginning, I mean, we all know why the design process is the way it is, and we all know why fees are small at the beginning. With tools like this, you can assess hundreds of options at an early stage without increasing the cost. And that is what we try to achieve. So invest more time, invest more effort at an early stage to create a better building. Will that lead to more costs at the beginning? Not always. I think in the near future, with how quickly things are happening, it will not lead to such higher increases at an early stage.
Okay. Got a question from Zoe Black now. Was AI used to do the models you describe? I was involved in modelling a building 25 years ago, which used computer modelling to analyse vent sizes, similar to the modelling you describe. What has changed now? Is AI used to improve computer modelling speed only? The answer to that specific question is no. It's not just about increasing computer speed. What we use to increase computer speed and modeling speed is not really AI. It's a few automation tools. It's a few scripts that make something parametric. In simple terms, for example, in the past, if you had to model one story, 25 stories, you'll have to model them possibly one at a time. With automated scripts, you can model one and replicate instantaneously. So what we use to make this modeling faster is not AI, it's just a bit of automation. What we use to analyze the results faster is also not AI, although we do use
some of these AI helpers to help us streamline the code. So we write code, and then sometimes we use AI tools to help us make it cleaner and easier to run, so that an analysis, instead of going into loops which might not be efficient, it's done faster. Where we use now AI now is to complete the data. So because in its most basic form, AI is an interpolation and a regression sort of relationship. So we have current data and we understand the trends, and we don't have to model every single point because we can infer it from the data that we already have. This is simple to understand when you've got a linear relationship or a 2D relationship, but when you've got a 3D or 4D relationship, that's where we use machine learning sequences. And the other thing that we use AI for is, once we have all that data, we start training it so that next time you don't have to model the whole thing, because it can predict based on the data that it already has. Hopefully that explains the process.
Okay, we've now got a question from Paul Hessen. Does the proposal you've outlined deliver a bland but efficient box onto which the architect or the client can then apply their design aspirations, with a loss of efficiency and knock-on effect to energy use, build costs, etc., provided in real time?
I think it provides, depending on what the parameters are, it can provide the most efficient solution on which the rest of the design team and the client and the architect can introduce other aspects to make it better. But it's not a bland box necessarily. One of the options could be a bland box. But depending on what parameters you define, the most efficient solution might be something incredibly complex and incredibly beautiful. If you define geometry, and if you define 3 variables of geometry, say X, Y, and Z, and that's all you have, you might end up with a box. But if you define geometry as a more complex algorithm, for example, we use this to design airport roofs. And an airport roof is not a black box, it's a complicated shape. We can use it to design bridges, which again are not bland boxes. So depending on what parameters you define, you can create really interesting starting points to grow from. But what you can say is that your starting point is the most efficient, let's call it bland box, to start with, or to start from.
Okay. We've got an anonymous question now from a QS. As a cost consultant, AI endears itself as a tool to use for real-time cost data, but how does the model work collaboratively with the cost application software to provide the client with their dream?
I think, there's lots different parts of that question. I think, yes, some AI tools, they want to be able to predict cost in real time. But if we analyze that sentence, predicting in real time, they predict because they have learned from a lot of data how something should look like. And then when they see something that is similar, this could be a building type, or it could be a construction process, they can go into the data that they have and predict in real time, because it's almost automatic. That is one aspect of using AI. How we are trying to use it is by, almost in real time, associate cost to the design decisions which are evaluated, so that then you can make a decision from the simulation. So you have a building that changes in shape and in orientation, and each of those has a rate that you apply from a cost consultant, and that rate informs that, and then you can choose that decision so that you can identify, this is what the client wants as a dream, and that's a cost consequence of that, and this is where we start. And how do we get to that dream? Can we get to that dream whilst we also meet all the other parameters? So it's not really using AI to create that assessment. It's using automation, it's using analysis, at an early stage with a little help from AI. So what we are doing is not analyzing tons of data to predict something yet. We are evaluating real assets with real models, with real simulations to achieve a certain performance, which is why I call this talk augmented intelligence, not just artificial intelligence. Maybe in the future, once we have analyzed every possibility, we'll have enough data that we won't have to design ever again because it's all predictable.
Okay. Lots of the questions we're getting this afternoon are from QS, as it would appear. I've got a question from John Griffiths. Is the answer to optimize design and cost and then not reinvent the wheel for every building going forward?
I think there is a market for every type of building. I think that when we look at a Bell distribution of buildings, there will be a vast majority of buildings where we don't need to reinvent the wheel. Absolutely not, because we know what works. We know what works in a certain soil, in a certain city, with a certain orientation. We know we need to make it more efficient, and that is how we bring costs down. But at the same time, we need to create cities. I mean, that's not the only factor that influences building design. It's also about the interaction with people. And cities like London do this incredibly. When you walk around the city, you see how buildings land and how buildings are experienced by people at a human level, at an eye level. And every single building is different. And the conditions of the basements and the conditions of the ground are different. And the views and the protected views are different. And the rights of light and height are different. So yes, we can try to find that for 80% of the projects. There will always be that extra 20% of buildings and a 20% of one building that needs an extra piece of uniqueness and value. Because in the end, buildings are much more than just space, right?
Okay, I think we have time just for one last question. This is from Anonymous. How do humans and AI negotiate a common objective in co-creative design processes, especially when human objectives like personalization and fairness often differ from AI's traditional performance or accuracy metrics?
Oof, I think...
Tough question for the last one, yeah.
I think the answer is in the question itself. It is, we need to tailor the objectives of the tools that we use. Let's not call it the AI, but the tools that we use, tailor those objectives to meet what we want to achieve. Because we need to focus on those objectives which go beyond just the material, the geometry, or cost, for example. If you can make something a parameter, you can assess it. Simple example, if you think about building shape, is all about geometry, is all about perspective, which is about a physical parameter. So how do you assess that? You could assess building beauty in relation to proportions and perspective as well. So there could be ways to align our values with those of the systems that we use to optimize them. And I think that is going to be fundamental to every industry and every discipline. We've heard all the stories of algorithms optimizing for negative things, that impact teenagers and mental health. What we need to do in our industry is make sure that the algorithms that we use are aligned with those values that we want to prioritize. That could be much more than just time, cost, and quality. They will be about fairness, it will be about bespokeness, and it will be about creating good, sustainable buildings.
Thanks very much, Diego. Thank you very much for your thoughtful and interesting presentation and for responding so eloquently to those somewhat difficult questions that the audience have posed to you this afternoon. I'd like to thank everybody for joining us in this webinar this afternoon, and that the video will be available on the JCT website, and the JCT will send you an email confirming that to you personally. Thank you again for joining us.